In this video, I'll talk about the torque acting on a dipole. First, let us understand what a dipole is. A dipole is a combination of two charges, negative charge and positive charge. Both has the equal magnitude, okay, minus q and then plus q. And it is separated by a distance r. So this system or this combination is called a dipole. The dipole moment is defined as this one is the dipole moment is defined as q times r, where r is the distance between the two charges, that is the dipole, and the direction of the dipole is from negative to positive charge. Okay, so this is the direction of the dipole. So now you might be wondering, why is the direction of the dipole is from negative to positive charge? Why not from positive to negative charge? Well, this is just a sign convention. In physics, we define the direction always from negative to positive charge, but there is one more logic behind this one, and I'll explain later that why do we select or why do we choose the direction of the dipole from negative to positive charge. That is, will be described in the later part of this video. Okay, so here is the magnitude of the dipole. Q is the magnitude of the charge and R is the separation between them. So here we're going to talk about what happens if we place a dipole in an external electric field. Okay, so here is the situation. So we have an external electric field, that's a uniform electric field between the two parallel plates. Okay, so the direction of the electric field is from positive to negative charge. So this arrow shows you the direction of the electric field, and here we have placed the dipole here. So again, this one has to be the direction of the this one will be the direction of the dipole, p vector. Okay, that's the dipole moment direction. So as we place the dipole into an electric field, there will be a force acting onto it. And why will be there a force? Because we already have talked about that the charge, any charge experiences a force into an external electric field, and this is given by this equation here. The force is given by the charge and the electric field, and this is the external electric field. So if there is a positive charge, then and let's say this is the direction of the electric field. So this here is the direction of the electric field. All right, and here in this case too. So this is the electric field. If we place a charge into an external electric field and if it is a positive charge, then the force and the electric field will be in the same direction. But if it is a negative charge, then the force will be in the opposite direction. And you can see here, if this is a negative charge, then force will be minus q times E. That means the force and the electric field are in opposite direction. So in this case, this is the direction of the electric field and the force will be in opposite direction. So let's talk exactly the same situation right here. So this is a positive charge. As this is a positive charge, the force and the electric field will be in the same direction, and this is the electric field direction. So this is the force direction, and onto this charge the force will be in the opposite direction. And you can simply also understand in a way, so this is a positive charge, so this positive charge will attract the negative charge, so the force of course will be in this direction. And this is a negative charge or this is a positive charge, so this negative plate will attract the charge, so this will be the direction of the the force. So we have now understood the force direction. But now let's see. As this charge, the magnitude of the charge here are equal, the magnitude of the force are also equal. So these two have equal magnitude. So the net force acting onto the system is zero. But there's one catch here. Although the net force is zero, but these forces are not on the same line of action. What does that mean? That means these forces are acting into a different lines. So let me draw this one. It will be much more clear. So I'm going to use probably some other colors. So for this one, the line of action is in this direction. Okay, and for this one, the line of action is in this direction. So these two are acting, these two forces have the different lines of action. So if there are two equal forces acting onto a system, the magnitude of the forces are equal, but the forces are not in the same line, then it will form a torque, or that means these two coupled forces will now rotate the system. In this case, it will rotate the dipole. That's what we call the torque. So there's a torque acting onto the system. So now let's find out what is the magnitude of the torque and how do we define torque. Okay, so as these two forces are equal in magnitude but not in the same line, this will form a torque. So how do we define the torque? The torque acting onto a dipole is given by this vector quantity. Torque is R cross F, and this is a cross product. Okay, so the cross, what does this mean? That means the torque, the direction of the torque is in the perpendicular to the plane of R and F vector. So it has to be perpendicular to both R and to the force F vector. So here, this is the R vector here, and this is the force vector. So it has to be perpendicular to both. And I will talk about how to find the direction. Okay. So the magnitude, if you already had taken the calculus class, you should be able to, you should be familiar to the cross product. So in this case, the magnitude of the torque is given by RF and sine theta. And theta is the angle between R and F vector. So in fact, R sine theta is the perpendicular distance between the lines of action of the two forces. So what does this mean? So if, let me draw into different color. So in this case, so this one, so this is the perpendicular distance, and this is the length R. So this length is R. So this length is R. So this length will be R sine theta, and this length here will be R cosine theta, and this angle is theta here. So again, as I mentioned, theta is the angle between R vector and the force vector. So this is the force and this is R. So this is the angle. And this R sine theta is the perpendicular distance between them. So once we know that, the magnitude of the torque, and we just plugging, we have to calculate in terms of electric field. And you already know that the force is equal to Q times E. So I'm just replacing this force by Q times E. So this force is now replaced by QE. Okay, and then remember this QR, the magnitude of the charge, and the distance between the two charges is the dipole moment. So here I'm writing P times E times sine theta. So this is the magnitude of the torque acting onto a dipole when we place it in an external electric field. So here, so you see that the torque is not a constant quantity. It is changing. It does have a sinusoidal nature. So the theta, the sine theta has a maximum value from 0 to 1, the magnitude. So when this dipole is perfectly aligned with an external electric field, just like in this case, so there is no torque. In this case, the torque will be 0. And where the dipole is aligned, in this case, this way, then there will be the maximum torque. So the magnitude of the torque is changing with respect to the time. So okay, the one time it will be 0 in this case, and the other time when it is aligned, it will be the maximum. So the torque varies sinusoidally. Okay. So now let's come back to our first the question why the dipole is chosen from negative to positive charge. So here let me explain this one. Again, this is just for convenience, okay, but in physics it is always chosen from negative to positive charge. When you have a dipole here, or in this case when it is at an angle theta and placed in an external magnetic field, the electric field tries to align the dipole in the direction of the electric field, and this will be the direction in this case. Okay, so this will be the most stable conditions here. So you see now the force, this force will try to rotate this way and this one. So the most stable case will be in this case aligning the electric field in this case here. So, and that's the reason we have chosen, or the physicist has chosen, the direction of the dipole from negative to positive charge. Okay, but I think in chemistry it is, I mean, you can equally choose from positive to negative. So this is just a sign convention. Okay, so but this so when you place in the an electric field, then this is the most stable case when the dipole is in perfectly aligned with the electric field. So in vector form, we can write down the torque in this way here, P cross E vector. And now let's find out what is the direction of the torque. So we have found out the magnitude. So what is the direction? So in order to understand the direction, first let's try to understand again, talk about the force. So these two forces will try to rotate this dipole in this direction here. Okay, so this will be the direction of rotation. So now in order to find out the direction, what you have to use a right hand rule. So this is the right hand rule. So what you have to do, you have to curl your finger in the direction of rotation. Then your thumb points out the direction of the torque. Okay, so let's apply here. So in this case, this is the direction of rotation. So if I curl my fingers in the direction of the curl, then the torque will be in this direction, perpendicular to the plane, or it will be in the plane here and perpendicular. So this direction is the direction of the torque, or into the paper will be the direction of the torque. So this is how we find out the magnitude of the torque and the direction of the torque on the dipole. Okay, and choosing the direction of the dipole moment is just for a sign convention. In physics, we use from the negative to positive charge. So this is it. If you have any questions, let me know. And please do not forget to like, share, and subscribe the channel. Thank you very much.